Let's start with a number because I think numbers more than anything else are what break people's hearts on this topic. The nearest star to our sun, Proxima Centauri, is about 4.24 light years away. Now, light year sounds like a unit of time, right? It's not. It's a unit of distance. It's how far light itself travels in one full year, moving at 186,282 meters per second, the fastest anything in this universe is allowed to move. And even at that speed, the literal speed limit of reality itself, it still takes over 4 years just to get a signal there. 4 years to the nearest star. Not a particularly interesting star, by the way. Not one. We've got a habitable planet confirmed around, though there's a small, tantalizing, rocky world in its habitable zone that keeps astronomers up at night. Just the closest one, the one right next door, cosmically speaking. So, here's the question I want to spend the next while genuinely unpacking with you. Why can't we just go faster? Why can't we build a better engine, a bigger rocket, some clever bit of 22nd century engineering, and just close that gap? And I want to be honest with you right up front because I think honesty is what you deserve on a topic like this. The answer isn't we haven't figured out the engineering yet. The answer is that the universe itself, at the level of its most fundamental geometry, appears to have built a wall around every star system, including ours. And that wall isn't made of steel or heat or radiation. It's made of physics. Actual foundational, this is how space-time works. Physics, and once you understand what that wall is actually made of, I think you're going to see the night sky completely differently. So let's build this up properly, because this deserves to be understood, not just accepted. Here's where I want to start with Einstein and with a num that I think is honestly one of the most underappreciated facts in all of physics. The speed of light isn't just really fast, is not simply the current record holder waiting for someone to come along and beat it. The way a 100-meter dash record gets broken every few Olympics. The speed of light is a structural feature of space-time itself. It's baked into the geometry of the universe. The same way the number of dimensions is baked in. The same way causality itself is baked in. Nothing with mass can reach it, let alone exceed it. And here's the part that I think really deserves your full attention. It's not that we lack a powerful enough engine. It's that as any object with mass approaches the speed of light, its effective mass, the amount of energy required to accelerate it, further increases without bound. Not increases a lot, increases toward infinity. Which means, and I want you to really sit with this, accelerating a spacecraft with actual astronauts on board to the speed of light would require an infinite amount of energy. Not more energy than we currently have access to. Infinite. There isn't a bigger battery. There, why reaching light speed requires infinite energy isn't a more efficient engine. There is no version of tomorrow's technology that gets around this, because this isn't an engineering limitation. This is the universe's own operating system telling you this door does not open under any circumstances for anything with mass. Now, a natural question you might be asking, and it's a great question, I get asked some version of this constantly, is, okay, fine, we can't hit light speed exactly, but can't we get close 90%, 99%? Wouldn't that be enough? And here's where I want to bring in the first genuinely mind-bending piece of this puzzle. Because getting close to light speed isn't just hard, it's hard in a way that keeps getting harder faster the closer you get. Let me give you a mental experiment. Imagine you've built the most efficient rocket engine physically possible, and I mean physically possible in the truest sense. Not just the best thing NASA's engineers can currently dream up, but the theoretical best. An engine converting mass directly into energy with perfect 100% efficiency, something we call a photon rocket, because it would literally be propelled by emitting light itself out the back, even with that theoretically perfect engine. Getting a spacecraft to 90% of the speed of light requires you to burn through a truly staggering fraction of your ship's own mass as fuel. And getting from 90% to 99% of light speed doesn't just require a little more fuel, it requires dramatically exponentially more because of that same relativistic mass increase we just talked about. Getting from 99% to 99.9% requires even more. Again, the closer you get to that ultimate speed limit, the more the universe seems to dig in its heels and demand exponentially more energy for smaller and smaller gains in speed. It's like running toward a wall that keeps getting harder to push against the closer you get to it. Right up until at the wall itself, the resistance becomes literally infinite. Here's a number that I think really drives this home. To accelerate a spacecraft with a mass comparable to, say, the International Space Station, up to just 50% of the speed of light, using a perfect photon rocket, you would need an amount of energy roughly comparable to the total energy output of the Sun over a period of several days. The Sunday, our entire star radiating at full blast for days, just to get one modestly sized ship up to half of light speed. And we haven't even gotten it to its destination yet. We haven't accounted for decelerating at the other end, which, and this is worth remembering, requires roughly the same staggering amount of energy all over again, because Newton's laws don't stop applying just because you're moving fast. You don't get a discount on stopping. Now, here's the thing, and this is where I want to introduce our first challenging pill of the night, because I don't want you to walk away thinking this is purely a fuel problem, purely an if only we had bigger tanks problem. Even if, and I mean this as a genuine thought experiment, suspending all practical objections, even if humanity somehow solved the energy problem completely, built some magical unlimited power source, there's a second wall waiting for us. And this one's arguably even nastier because it's not about energy at all, it's about what's actually sitting in the space between the stars. We tend to picture interstellar space as this perfectly empty void, right? Nothing out there, just vacuum stretching on forever. And it's true that it's an extraordinarily good vacuum by Earth standards, emptier than anything we can create in any laboratory on this planet. But extraordinarily good vacuum is not the same thing as completely empty. And at the speeds we're talking about, that distinction becomes lethal. Here's why. Interstellar space contains what we call the interstellar medium, trace amounts of gas, mostly hydrogen along with scattered dust grains, remnants of long-dead stars, and stellar winds, all drifting through the space between star systems at very low densities. On average, we're talking about roughly 1 atom per cubic centimeter in the interstellar medium, spectacularly sparse compared to the air you're breathing right now, which has something like 10 billion molecules crammed into that same volume. So, it sounds negligible, right? It sounds like something you could just ignore, except, and here's the challenging pill, at relativistic speeds, even that sparse handful of atoms becomes a genuine spacecraft-destroying hazard. Think about it this way. If your ship is moving at, say, 90% of the speed of light, then from the ship's own frame of reference, every single hydrogen atom drifting in interstellar space is now slamming into your hull at 90% of the speed of light. And at those velocities, individual hydrogen atoms stop behaving like harmless, gentle wisps of gas and start behaving like high-energy cosmic radiation. Similar to the kind of particle radiation we get from cosmic rays, except now it's not an occasional high-energy particle punching through your shielding. It's an absolutely relentless, continuous bombardment, because your ship is now effectively plowing through a very thin but very fast-moving stream of radiation for the entire multi-year duration of the voyage. Calculations on this, and this is genuinely sobering, suggest that an unshielded spacecraft traveling at a meaningful fraction of light speed toward Alpha Centauri would receive a lethal, potentially even structurally damaging dose of radiation from these interstellar medium collisions well before it ever arrived. And it's not just the hydrogen atoms. There's just 2 tiny grains, sometimes just a few microns across. But at relativistic velocities, a dust grain carries kinetic energy comparable to a bullet or worse. A dust grain, the size of a grain of sand, hitting your hull at even a modest fraction of light speed could deliver an impact energy equivalent to a small explosive charge. An interstellar space medium. The interstellar medium, deadly at high speed over trillions of miles of transit, is guaranteed to contain some number of these grains directly in your path, statistically speaking, whether you like it or not. So now you've got two independent walls, both erected by fundamental physics rather than mere engineering shortfalls stacked directly on top of each other. Wall number one, the energy required to reach relativistic speeds approaches infinity as you approach light speed itself. Wall number two, even if you somehow get close to light speed, the interstellar medium itself becomes a lethal continuous radiation and impact hazard. Specifically because you're moving that fast. Go slower and you dodge wall number two. Sure, but then you run headlong into an entirely different problem. One that's got nothing to do with energy or radiation and everything to do with something far more human, time. Because here's the number that I think should genuinely stop you in your tracks. Even traveling at a wildly optimistic 10% of the speed of light, a speed we have exactly zero current technology capable of achieving for a crewed vessel. By the way, the trip to Proxima Centauri alone would take over 42 years. One way, not a weekend trip, not even a career-length mission, a multi-generational undertaking where the people who launched the mission are almost certainly not the people who would arrive, and the people who arrive were never the ones who made the decision to go. Now, let me give you an everyday connection because I think this is where the true gut-level scale of this problem really lands. Imagine you're standing at one end of a football field, an American football field, 100 yards goal line to goal line, and I ask you to represent our entire solar system from the sun out to Pluto's orbit with a single grain of sand at your feet. On that same scale, using that same football field, where do you think the nearest star would be? Not the end zone, not the far goal line, not even close. On that scale, the nearest star would be roughly 4,000 miles away. 4,000 miles. That's roughly the distance from Los Angeles to London. That's the true proportional emptiness of the space between star systems. And it's not a quirky fact. It's the entire reason this problem is so brutally fundamentally hard. We're not just dealing with far. We're dealing with a scale of emptiness that makes far feel like an inadequate word entirely. And here's a piece of dark humor for you because I think you need it right about now. If an alien civilization somewhere out there is watching us through some kind of telescope and they've correctly worked out the actual scale of interstellar distances and they're watching movies where spaceships casually zip between star systems in the time it takes to have a conversation, they're probably reacting the same way you would if you watched a movie where somebody swims across the entire Pacific Ocean in an afternoon wearing regular street clothes and nobody in the film even mentions it as remarkable. It's not just wrong, it's a scale of wrong that borders on comedy. So where does that leave us? We've got a speed limit baked directly into the geometry of space-time, an interstellar medium that turns into lethal radiation, and shrapnel at relativistic speeds, and distances so vast that even our most optimistic sublight speeds turn single journeys into multi-generational sagas. And I haven't even told you yet about what happens to time itself for anyone actually attempting this journey, because it turns out the faster you go, the stranger your relationship with the rest of the universe becomes in ways that Einstein himself found almost too strange to fully believe at first. That's where we're headed next. So, we left off with this staggering scale, problem distances so vast that even our best hypothetical speeds turn into multi-generational commitments. Now, here's where things get genuinely deeply weird, because it turns out that even if you could survive the radiation, dodge the dust, and somehow fund a spacecraft capable of sustained relativistic acceleration, the universe has one more surprise waiting for you, and it's baked directly into the fabric of space-time itself. Time dilation. Here's the deal, and I want to build this up carefully because this is genuinely one of the most beautiful and most disorienting consequences of Einstein's special relativity. Time is not a universal fixed backdrop against which everything happens at the same rate for everyone. Time is relative to your speed. The faster you move through space relative to some other observer, the slower time passes for you relative to that observer. This isn't a philosophical statement. This isn't a metaphor. This has been measured repeatedly with atomic clocks on airplanes, with particles in accelerators, with GPS satellites that literally have to correct for this effect every single day just to keep your phone's map from drifting miles off course. Time dilation is real. It's measurable. And at relativistic speeds, it becomes dramatic. So here's a mental experiment I want you to really sit with. Imagine a crew departs on a mission to a star system 20 light years away, traveling at a sustained 90% of the speed of light again, wildly beyond anything we can currently build. But let's suspend that for the thought experiment. From the perspective of everyone back on Earth, that trip takes a little over 22 years one way, accounting for acceleration and deceleration. But from the perspective of the crew themselves aboard the ship, experiencing time dilation, the trip might feel like it only takes around 10 years. Their clocks, their biological aging, their own subjective experience of time, all of it runs measurably slower relative to Earth because of how fast they're moving relative to Earth. The true scale of interstellar distances. Now here's the challenging pill, and I think this is where interstellar travel stops being just a hard engineering problem and starts becoming an almost existentially strange one. If that crew turns around and comes home still at relativistic speeds, they might arrive back on Earth having aged only 20 years subjectively, but back on Earth, depending on the specifics of the trip, 44 years or more could have passed. Everyone they knew, parents, siblings, friends, entire social and political context would have aged decades beyond them, or in more extreme scenarios involving speeds even closer to light. Generations could pass on Earth while the crew experiences only a handful of years. This effect has an actual name borrowed from a French novel that explored exactly this idea. We call it the twin paradox, where one twin stays on Earth and ages normally, while the other twin takes a relativistic journey and returns younger than their sibling, not because of some biological quirk, but because they have quite literally experienced less time. Let me give you an everyday connection for this because I think it helps the stranges land properly. Imagine you and your best friend from childhood. Let's use George and Gracie again because I love using them for this. Imagine George stays on Earth, living a completely normal life, while Gracie boards a relativistic starship for what feels to her like a 10-year round trip to a nearby star system and back. When Gracie steps off that ship, expecting to reunite with her old friend George, she doesn't find the George she left behind. She finds an 80-year-old man, if he's even still alive, because more than 40 years have passed for him, while Gracie has barely aged into her 30s. Every person Gracie knew before she left has moved forward through decades of life without her. The technology has changed. The culture has changed. The entire world she returns to is not the world she left, even though from her own subjective experience, she was only gone for about a decade. This isn't science fiction license. This is the honest, mathematically rigorous prediction of special relativity confirmed again and again in smaller scale experiments here on Earth. And here's what I think is the deepest, most quietly devastating implication of all this. Relativistic time dilation doesn't make interstellar travel impossible in a technical sense. In fact, in a strange way, it's almost a mercy, because it means a crew could in principle subjectively experience a journey to a distant star as taking a survivable handful of years rather than the many decades or centuries an outside observer would measure. But that mercy comes at a brutal cost. It severs any traveling civilization from the civilization that sent them. A colony ship leaving Earth for a star system 50 light years away isn't just leaving behind their families and their culture. Depending on their cruising speed, they might be leaving behind their entire historical era. Any return trip, any continued communication, any sense of remaining part of the same ongoing human story back on Earth becomes fundamentally physically strained by this mismatch in the flow of time itself. You don't just travel through space on a journey like this. You travel unevenly through time relative to everyone and everything you left behind. And there is no version of physics that lets you have it both ways. You cannot move fast enough to make the trip survivable within a human lifespan without also creating this profound temporal separation from home. Now at this point I know some of you are thinking about the loopholes, the greatest hits of theoretical physics, wormholes, warp drives, the stuff that makes for great science fiction, and frankly, wonderful late-night physics conversations. And I don't want to dismiss these because they're genuinely fascinating, legitimate areas of theoretical research. But I do want to give you the honest, unflinching status report on where they actually stand, because there's a massive gap between mathematically permitted by general relativity and achievable by any civilization we can currently imagine building. Let's take the Alcubierre warp drive first proposed by physicist Miguel Alcubierre back in 1994. The concept is genuinely elegant. Rather than moving your spacecraft through space faster than light, which remember is strictly forbidden, you instead contract space in front of your ship and expand space behind it, effectively surfing on a wave of distorted spacetime itself. Your ship locally never exceeds the speed of light within its own little bubble of normal space. But that bubble riding this wave of contracted and expanded spacetime could in principle carry you to a destination faster than light would take to get there through ordinary uncontracted space. It's a beautiful bit of mathematics. It's fully consistent with the equations of general relativity. And here's the challenging pill. It requires a form of matter with negative energy density, something we call exotic matter. And here's the honest truth. As of right now, in your lifetime, we have no confirmed evidence that macroscopic quantities of this kind of exotic matter can even exist, let alone be manufactured, contained, and controlled, at the staggering scale and stability required to actually warp spacetime around a spacecraft. Some theoretical work has suggested the energy requirements, once thought to be greater than the mass energy of the entire observable universe, might be reducible with clever geometry. And that's genuinely exciting, genuinely worth continued research. But reducible doesn't mean achievable. We're talking about a gap between theoretical permission and physical construction that may honestly never close, or may time dilation and the twin paradox take discoveries in fundamental physics we cannot currently even anticipate. Wormholes carry a similar story. Solutions to Einstein's equations that describe shortcuts through spacetime connecting two distant points via a kind of tunnel do exist mathematically. They're called Einstein-Rosen bridges, the first identified back in 1935. But every physically realistic model we've developed suggests these wormholes would be catastrophically unstable, collapsing on timescales far too short for anything, let alone a spacecraft to pass through. Unless, again, you introduce exotic matter with negative energy to hold them open. Same fundamental roadblock, same gap between the math allows it and the universe, as far as we can tell, actually provides the raw materials to build it. So, here's where I want to land this second act of our story, because I think it deserves to be stated plainly. Interstellar travel isn't hard the way, say, curing a disease is hard, where we can point to a research pathway and reasonably expect progress within decades. It's hard the way it would be hard to build a ladder tall enough to climb past the edge of the observable universe. At some point, you're not looking at an engineering gap anymore. You're looking at a gap between what our universe's fundamental laws seem to permit and what those same laws seem to actively structurally forbid using tools and materials. We have zero confirmed evidence even exist in usable form. And that brings us to the deepest, most philosophically loaded question in this entire story. The one I think about more than almost any other question in my professional life. If these barriers are real, if the energy requirements truly do approach infinity, if the interstellar medium truly is lethal at relativistic speeds, if time dilation truly does sever any traveling civilization from its origin, then what does that mean? Not just for us, but for the possibility of any advanced civilization anywhere in this galaxy ever meaningfully visiting another star system. That's where we're headed for our final act tonight. Because it turns out this isn't just a story about human limitations. It might be one of the most important clues we have about why the universe looks the way it does. So, we left off staring down one of the most humbling implications in all of physics. If these barriers to interstellar travel are truly fundamental, truly baked into the geometry of space-time, rather than merely reflecting our current technological limitations, then they don't just apply to us, they apply to everyone. Every hypothetical civilization anywhere in this galaxy, orbiting any star, evolving on any world, would be bound by the exact same laws of physics we've spent this whole story unpacking. And that single realization connects directly to one of the most famous open questions in all of science. You've probably heard some version of the Fermi paradox. This deceptively simple question, first posed informally by physicist Enrico Fermi back in 1950, that basically boils down to, given how old and how vast our galaxy is, containing hundreds of billions of stars, many of them billions of years older than our own sun, where is everybody if intelligent technological civilizations are common? Shouldn't at least some of them have had more than enough time to spread out, colonize, explore, make their presence unmistakably known? And yet, as far as our best instruments can tell, after decades of dedicated searching, the galaxy appears profoundly, almost eerily silent. There are a lot of proposed explanations for this silence. Some genuinely disturbing, some more hopeful. Maybe intelligent life is simply staggeringly rare. Maybe civilizations tend to destroy themselves before they achieve interstellar capability. But here's the explanation I want to focus on tonight, the one that connects directly to everything we've built up over this entire story. Maybe civilizations don't need to be rare, and they don't need to be self-destructive for the galaxy to appear silent. Maybe the galaxy looks empty of interstellar travelers because interstellar travel in any meaningful civilization scale sense is simply physically off the table for absolutely everyone, everywhere, always. It's not because nobody's clever enough to attempt it, but because the universe's own geometry makes the attempt fundamentally mathematically unworkable at scale for any civilization bound by the same laws of physics we're bound by. Here's the challenging pill I want to leave you with tonight, and I think it might be the most profound one in this whole story. The same laws of physics that govern the motion of planets, that predicted the bending of starlight during a solar eclipse, that gave us GPS and nuclear power, and an understanding of black holes so precise we've now literally photographed one. Those same laws appear to be quietly, elegantly, ruthlessly enforcing a kind of cosmic quarantine. Not maliciously, not deliberately in any sense that implies intention, simply as an emergent structural consequence of how space-time itself is built. Every civilization on every world orbiting every star may simply be permanently physically isolated within the boundaries of its own solar system. Not because someone built a wall to keep them in, but because the geometry of the universe itself never provided a door. And I want to be careful here because I don't want to overstate our certainty. We haven't proven interstellar travel is definitely permanently impossible. We've identified genuinely staggering, currently insurmountable barriers grounded in physics we trust enormously. But the history of science is also full of moments where impossible quietly became not yet understood. I'm not going to sit here and tell you that in 500 years, or 5,000 some future civilization, possibly even our own descendants, won't have found some genuinely new physics, some structural loophole in space-time we haven't even conceived of yet. That changes this entire conversation. Science doesn't deal in permanent absolute certainty about the unknown future of physics itself. But I am going to tell you honestly that based on everything we currently understand about energy, about relativity, about the actual physical contents of interstellar space, the barriers we've walked through tonight are not modest. They are not, give it a few more decades of engineering barriers. They sit right at the foundation of how this universe is built. Let me bring us back around full circle to where we started. Remember that light-year figure? 4.24 light-years to the nearest star? I want you to hold that number next to everything we've since learned. The energy cost that approaches infinity as you near light speed, the interstellar medium turning into lethal radiation at relativistic velocities, the staggering, almost incomprehensible true scale of interstellar emptiness, that football field with a grain of sand at your feet, and the nearest star 4,000 meters away. The way relativistic time dilation could let a crew survive the subjective journey only to sever them from their entire civilization back home in the process. Wormholes, warp drives, and exotic matter. And finally, the exotic matter required for warp drives and wormholes, theoretically permitted, but with zero confirmed evidence it can ever actually be built, held, or controlled. Here's what I want you to sit with as we close tonight. And I think it's worth genuinely feeling this, not just intellectually understanding it. Every star you can see in the night sky, every single one, is not just far away. It's separated from us and from each other by a barrier woven directly into the mathematics of reality itself. And that might sound on the surface like a deeply depressing conclusion. A universe of hundreds of billions of galaxies, each containing hundreds of billions of stars, and every single one of us, wherever we happen to have evolved, is permanently physically marooned within our own tiny corner of it. But I want to offer you a different way to feel about that, because I genuinely believe this, not just as a nice sentiment to end a show on, but as something close to how I actually think about our place in the cosmos. If it's true, if every civilization really is isolated within its own solar system by the unbreakable geometry of space-time, and that makes Earth and everything happening on it right now extraordinarily, almost unbearably precious.
We are not one node in some galaxy-spanning network of easily interconnected civilizations.
We may well be an island, a genuinely isolated pocket of consciousness, awareness, curiosity, and wonder, floating in a cosmic ocean so vast that even the nearest other shore, if it exists at all, might be permanently physically unreachable. And rather than that making our exploration of the universe feel smaller, I think it should make it feel more urgent, more precious, more worth doing well. We can't physically cross those distances, at least not with anything resembling ease, maybe not ever, but we can still look. We built telescopes that let us see light that left distant galaxies before Earth even existed. We've sent robotic ambassadors past the edge of our own solar system, carrying golden records of who we are, drifting now through that same interstellar medium we described as lethal, on journeys that will long outlast our species, on the infinitesimally small chance that someone someday, somewhere finds them. We may never physically walk on a planet orbiting another star, but we can understand it. We can measure its atmosphere from trillions of miles away, using nothing but starlight passed through its air. We can know things about worlds we will never touch. And I happen to think that's one of the most extraordinary achievements a physically isolated maroon species could possibly manage. So the next time you look up at the night sky and your eye catches on some faint, unremarkable point of light, remember that it might be permanently physically unreachable, sealed off from us by the very geometry of the universe we live in. And then remember that we found a way to know it anyway. We measured its light. We calculated its distance. We wondered about it seriously, rigorously together, even knowing we may never set foot there. That, to me, is the real story here. Not that the universe built walls around every civilization, but that even from behind those walls, we never stopped looking outward anyway. Keep looking up.